Welcome. We're talking about chemical bonding this week. We know that we have ionic bonding and covalent bonding. Now, with ionic bonds, we have that transfer of electrons to form ionic compounds. Or with covalent compounds, we can share electrons. Atoms will continue to react until they reach a stable configuration, which is sharing 8 electrons for your covalent compounds or transferring electrons for your ionic compounds. The reaction will continue to happen until you reach that noble gas configuration of 8 electrons. The properties of compounds can be predicted if we know the type of bond that is formed between them. Now, compounds can actually be partly ionic and partly covalent. You can have the sharing of electrons, but it might not always be equal. So think about a candy bar and your sibling, and you cut it in half, but it's not exactly half. And you give your brother the smaller half. I've tried to combat that by saying you could cut and then the other gets to choose which half. And so then they try to make it more equal. But electrons aren't always shared equally among atoms. We talked about electronegativity before and the trends in the periodic table with electronegativity. So if an atom with a high electronegativity is sharing with an atom that doesn't have as great electronegativity, you're going to have an unsharing or unequal sharing of electrons. Now, the properties of a compound are related to how equally the electrons are shared. If you have a purely ionic bond, that means you have complete unequal sharing. You have zero sharing. It's actually a transferring of electrons. That's what happens between metals and nonmetals. If you have a purely covalent bond, it's complete equal sharing of electrons. Now, most compounds have some ionic characteristics and some covalent characteristics. This is called a polar covalent bond. Now, there is a range of electronegativity differences to determine what type of bond you have. So if the difference between electronegativities is between 0 and 0.5, it's going to be nonpolar covalent. But if your electronegativity difference is between 0.5 and 2.0, it's going to be polar covalent. If it's that electronegativity difference is greater than 2, then it is an ionic bond. And that means, of course, that there is that complete transfer of electrons. So this is the same range that I gave you on the previous slide. And if we look, we want to know what type of bond is one between oxygen and fluorine. What type of bond is one between carbon and hydrogen? What type of bond is one between hydrogen and hydrogen? We'd have to calculate, we'd have to look up the values and determine what it falls in right here. But I can tell you right now that anytime you have an element bonded to itself, it's always going to be nonpolar covalent because they're going to have the exact same value. And anything subtracted by itself is 0. So all the Hofbrinkels, hydrogen, oxygen, fluorine, bromine, iodine, chlorine, and all of these are your diatomic elements. So whenever they're bonded to themselves, they're going to be nonpolar covalent. Now, bonding is similar to a tug of war for shared electrons. Electronegativity is a measure of the ability of an atom in a bond to attract electrons. Now, atoms are assigned electronegativity values, and those values, those with large values, attract shared valence electrons more strongly than atoms that have smaller electronegativity values. So if we had the question again, what type of bond is between carbon and hydrogen, you would look and you'd find carbon here, which is 2.5, and you'd subtract hydrogen's value, which is 2.1, and your difference would be 0.4. Then you'd use that range of values I gave you to determine what type of bond this is. And we had a nonpolar because it's less than 0.5. So CH is considered a nonpolar bond. Now, if we wanted to do OF, if we had an OF bond, that would be our 4.0 minus 3.5, and that would give you 0.5. And that would be a polar covalent bond. Because anything between 0.5 and 2 is polar covalent. So you will need to refer to this chart so that you know the electronegativity values whenever you're determining bond type. Now, electronegativity decreases down a group and increases across a periodic table from left to right, if you remember from last week. Fluorine has the highest value of 4.0, which is, and the lowest values are in the bottom left corner of the periodic table. So if we look at the periodic table, we talked about how fluorine was the most electronegative atom, and francium was the least electronegative atom. So the nonmetals are more electronegative than your metals. Now, the decrease in electronegativity down a group occurs because of the shielding effect. Remember, the larger the electrons, or the larger the atoms, the farther away the electrons are, so they're held less tightly, and then the inner electrons tend to block the attraction of the nucleus for the valence electrons, which means they're lost more easily. Now, the greater the difference between the electronegativities of the bonding atoms, the more unequally the electrons are shared. We calculate the electronegativity difference by subtracting the smaller electronegativity from the larger. So the change, this delta represents change, and the electronegativity, En stands for electronegativity, is always positive. So the electronegativity difference for cesium and francium is 4.0 minus 0.7, which is 3.3. Or cesium and fluorine, forgive me, is 3.3. So this is an ionic bond. Now, when the electronegativity difference is greater than 2.0, you have the sharing of electrons is not even possible. So there's a complete transfer of electrons. And that's whenever you get your ionic bond. Anytime you have a metal and a nonmetal, that electronegativity difference is going to be greater than 2.0. The greater the distance between bonding atoms on the periodic table, the more ionic the bond will be. Sodium and chlorine are on opposite sides of the periodic table if we looked at that. So you can see here, opposite ends, they're going to be ionic. The closer they are together, the more likely it is that they're going to be covalent. It might be polar covalent, it might be non-polar covalent, but it's going to be a covalent bond the closer they are. Now, when there's no difference or very little difference in electronegativities, you have a purely covalent bond. That would be all your diatomic elements because they're bonded with itself. So there's not going to be any difference. So when the electronegativity difference is less than 0.5, it's considered a nonpolar covalent bond just because it has a very slight unequal sharing of electrons. Now with polar covalent bonds, you have an electronegativity difference that's greater than 0.5. And that's a large unequal sharing of electrons. And it's called a polar covalent bond because you actually have a partial transfer of electrons to the more electronegative atom. So let's look at a water molecule, for example. So if we have a water molecule, this is a polar covalent bond. Oxygen is a higher electronegative value than hydrogen. Oxygen has a really strong electronegativity, electron affinity. So the electrons are actually pulled closer to the oxygens. If it's like a tug of war game, so it pulls the electrons closer to it. As it does, it gives the oxygen a slight positive or negative pole. So that's why it's called polar, because you have poles. The hydrogen, because its electron is pulled closer to oxygen, will have a positive pole. So that's what it means by partial transfer of electrons. It's sharing, hydrogen sharing its electrons with oxygen, but oxygen pulls it closer to it. It says, thanks for sharing. I'm going to keep it close to me. I have more electrons. I'm keeping it close. So the hydrogen is fine and it's still in a bond and its sublevel is filled now. So it is happy just to be able to have that complete S sublevel. And it's fine, but the electron is farther away from it in that bond. And so that's why you have that little bit of positive charge. It's like trying to share a bed with somebody and they steal the blankets. My kids will crawl in with me sometimes and that's what they do. They pull the blankets off. That would be an example of a polar covalent bond. You still have some of the blankets, but they have most of them. And you have very little. Now, polar covalent bonds are bonds that form when electrons are shared unequally, and they have significant ionic character. So you definitely have a positive pole and a negative pole. It's not a complete transfer, but you still have charges within the atom, the compound itself. So polar covalent bonds are called polar because of that unequal sharing of the electrons in the bond. So here we have hydrogen fluoride, and fluorine is very electronegative. It has a great electron affinity, and so it pulls the electrons closer to it. And that gives it the negative pole of the bond, whereas the hydrogen is left with its proton right here, and it's not as close, so it just has that positive pole over it. Because the electrons aren't shared equally, it's held more closely by the fluorine ion. Now, the negative pole is centered on the more electronegative atom, and the positive pole is on the less electronegative atom. Polar covalent compounds have different properties from nonpolar covalent compounds. The melting points are going to be different. So polar covalent compounds are going to have higher melting points. Because of those poles, they'll be attracted to each other a little more strongly than a nonpolar covalent. Something with even slight charges will be held more strongly together than something that doesn't have any charges. So water and carbon disulfide are both covalent compounds, but water is a polar covalent compound. So it has a 100 degrees Celsius boiling point. But carbon disulfide will boil at 46 degrees Celsius. So those bonds can be more easily broken in nonpolar covalent compounds, which means it has a lower boiling point because it doesn't have as strong intermolecular forces. So let's do a practice one. We'll do a few of them. I want you to try these out and then come back whenever you've completed it, and then you can check your answers. So here, what type of bond is formed between hydrogen, which is 2.1, and oxygen, which is 3.5? So you're going to take your 3.5 minus your 2.1, and you're going to get 1.4. This would be a polar covalent bond. That's what it falls into. What's the electronegativity difference between sodium, 0.9, and chlorine, 3.0? So 3.0 minus 0.9 gives us 2.1. That's greater than 2. So that's going to be your ionic bond, but that answer is C. If I had asked you to determine what type of bond this is, it would be ionic, because remember, it's 0 to 0.5. This is your nonpolar covalent bond. 0.5 to 2.0 is your polar covalent bond. And then anything between 2.0 and 3.3 is ionic. Now, which pair of atoms will form a nonpolar covalent bond? So if we're looking for a nonpolar covalent bond, we want it to fall within 0 to 0.5. So if we look at A, that's 3.0 minus 2.1, and that gives us a 0.9. That's too high to be a nonpolar covalent bond. We look at C, 3.5 minus 2.5. That gives us 1.0. That's also too high. If we look at C, 3.0 minus 3.0, that gives us 0. So this right here is our nonpolar covalent bond. A and B both fall within the polar covalent bonds. D would fall as an ionic bond because that would give you 3.1 as an electronegativity difference. So let's look at 4. The bond in hydrogen fluoride is considered what? So let's look at this. We have 4.0 minus 2.1. That gives us 1.9. So this falls in the line of polar covalent. It's still a covalent bond, but it's very unequal sharing. Let's look at bonding in metals, because this is a very different type of bond. Now, metals and alloys are malleable and ductile. And an alloy is just a mixture of metals. So sterling silver or 22 karat gold, those are alloys. Sometimes you add impurities to gold, for example, to make it stronger. So pure gold is extremely soft. West Virginia's state capitol, their dome is gilded in gold leaf because it's pure gold, and it's really, they call it leaves of gold that you just put over whatever it is that you want to cover, and it molds to that. And so it's really malleable, really soft, and you don't want your jewelry to be that soft to be able to get dented that easily. So that's why you get typically 18 karat gold or 22 karat gold, not 24 karat gold for your jewelry. Now, metals are malleable, and that just means that they can be pounded or rolled into sheets. Ductile means that a metal can be drawn into thin wires. And they are very conductive. And conductivity just is a measurement of how easily electrons can flow through a material to produce an electric current. That's why electricity is called electricity, because it's the flow of electrons. The lower the resistance, the better conductivity you have with your metal. Now, metallic bonding is very unique because the valence electrons of the metal atoms are very loosely held by the positively charged nucleus. This enables the metals to form what's called a metallic bond. There's basically a sea of electrons that surrounds the metal's nucleus. And those electrons are easily moved from one atom to the other. So whenever we look at metals, if you look down here, you can see that we have the nuclei in the orange, and that, of course, the nuclei are all positively charged because it just has the protons and the neutrons in it. But you have the electrons around it. And these electrons can flow from atom to atom, or from nucleus to nucleus, and because they're so loosely held. And this is why metals are such good conductors of electricity, because of this sea of electrons that we have in metallic bonding. The valence electrons aren't specifically attached to just one metal atom, so they do move easily throughout the metals. Now, there's something about compounds and their shapes that determine their properties. And we're going to concentrate on the molecular shape and polarity and the bonding so that we can better understand the properties of different compounds. So we can have three types of bonds. We can have single bonds, which are composed of two electrons. You can have double bonds, which are shorter than single bonds, because again, you have more electrons being shared, and they're composed of four electrons. Or you can have triple bonds, and they're even shorter than double bonds. They're the shortest bond type of all. They're held very tightly, and they have 6 electrons as part of the triple bond. Alkanes are molecules that contain only carbon and hydrogen, and they're composed of only single bonds. Methane is an example, and if we wanted to draw it, remember we drew some Lewis dot diagrams earlier, and we just say, well, I'd look at the periodic table, see what group my elements are in. So if we looked here, we have carbon in group 14. That means it has 4 valence electrons. And we have hydrogen in group 1. That means it has 1 valence electron. Okay. And we know carbon has 4 valence electrons, so we do 1, 2, 3, 4. There are actually 2 carbons, so those are going to be in my center. And then we have 6 hydrogens that have 1 hydrogen each, or 1 valence electron each. So we have 1 with its valence electron, another here with its valence electron, another here and its valence electron, here, here, and here. And then we just check to make sure the octet rule has been satisfied for both of them. Now remember, hydrogen and helium only need to have 2 because they only have the S sublevel. And the S sublevel can only hold 2 electrons. So this hydrogen has 2, this hydrogen has 2, this hydrogen has 2, this one has 2, this one has 2, and this one has 2. So those hydrogens all are good. They all have their octet rule satisfied. Now let's look at how many each carbon has. This has 2, 4, 6, 8. So this carbon is good. This one has 2, 4, 6, 8. So this carbon is good as well. So now we have our Lewis dot structure, and we can see that they all have single bonds. Here's a single bond, single bond, single bond, single bond. Single bonds only have 2 electrons. There's another way to write this. You could also draw a single bond represented by a line. If you didn't want to draw the dots after you had it all drawn, you can use the line to indicate a single bond. And if you have a double bond, you could use a double bond, a double line. If you had a triple bond, you just write the triple lines right there. Now, alkenes are molecules that contain only carbon and hydrogen, and they have a double bond in between them. So here we have the double bond in alkenes. So instead, it would look like this. So alkenes have at least one double bond right there. When we look at intermolecular forces, one particular force is the dipole-dipole attractions. And these occur between polar molecules. That's why it's dipole-dipole. The dipole occurs between polar molecules. So the positive end of one molecule is attracted to the negative of another. So if we draw our water molecule again, remember, oxygen's more electronegative, so it pulls those electrons closer to it. But in water, the molecules are held together by this dipole-dipole interaction. So this positive charge on a hydrogen is attracted. That's why I did these dotted lines. It's attracted to this positive charge on the hydrogen. So the positive hydrogen is attracted to the negative oxygen pole, and that's how they're held together. And that's why water has a high boiling point for a molecule its size. You have hydrogen bonding, which is what happens in water, and that's just a special case of dipole-dipole attraction. The hydrogen must be bonded to a highly electronegative atom like nitrogen, fluorine, or oxygen. And as I said, that attraction is represented by these dotted lines connecting the hydrogen bonded hydrogen to the unshared electron pair of the electronegative atom. Van der Waals, or London dispersion forces, is another type of intermolecular force. And these occur between nonpolar molecules. So this is how molecules of fluorine gas are held together, or molecules of oxygen gas are held together. They're caused by temporary dipoles, which exist in all molecules, both polar and nonpolar. It's a temporary pole because it's caused by the movement of the electrons within the electron cloud. So remember, you've got your electron cloud. So here's our nucleus. And you have your electrons, and your electrons are constantly moving. And if they all end up temporarily in one area for that split second, you're going to have a negative charge here and a positive charge there. But because your electrons are constantly on the move, that's why it's a temporary dipole. And it doesn't last very long. It's really weak. And you have these temporary dipoles in all molecules, both polar and nonpolar, but they're what drives the London dispersion forces. You can call them van der Waals or London dispersion forces. It's the same thing. It just depends on the text as to what term they use for it. So in this case, the temporary dipole causes an attraction between the two molecules, just at that split moment. And there will be constant temporary dipoles within the molecules as those electrons constantly move. It's like everybody's in this room, great, but everybody moves over to the left side of the room. So we're all crowded on that side. And then we decide, wait, it's too crowded, let's spread out again. And you might have more people in one area than another, but that area would just temporarily get that extra negative dipole until you start wandering around some more. A dipole-induced force occurs between polar and nonpolar molecules. So if we had water with sugar, for example, you would have a dipole-induced force because water's polar, sugar is not, but it would induce another dipole because the electrons from the oxygen that's close to the molecule would drive the the electrons in the sugar molecule away to the other side, creating a temporary dipole. Now, the attraction increases with increasing molecular mass. So as the molecular mass increases, you're going to have more of an attraction, a stronger attraction. So let's do some practice. Take a minute to answer these questions and then come back whenever you have finished and check your work. So here we have which type of intermolecular force is present in all molecules, including nonpolar ones. We just went over that, and that was our London dispersion forces. Dipole-dipole forces, these are in your polar molecules. Hydrogen bonding is a special type of dipole-dipole force, and that involves hydrogen bonding with oxygen, nitrogen, or fluorine. And then you have dipole-induced, and this is between polar and nonpolar molecules. The polar molecule will induce or force a pole in the nonpolar molecule. Now, what type of intermolecular force exists between a polar molecule and a nonpolar molecule? So polar and nonpolar, this is your dipole-induced pole. Which factor increases the strength of London dispersion forces? And that would be a larger molar mass. The greater the molar mass, the more electrons you will have. The more electrons you have, the more likely you are to have multiple temporary poles. If you have questions, let me know. I'm happy to help.